We are Smart World Systems, Inc. Today we'll discuss the creation of one of our products. Our core executive team includes Laurel Morris, me, Lily DeCamp, and Howard Lynn. This is a picture of our team working together to create our data sensing product.
For methods and data collection, we had to combine a series of skills and applications from mini projects 3 and 4 to collect data from 5 separate locations, create a hypothesis around relationships of interest, analyze data, and model it in AnyLogic. Here's an overview of our methods. We had to learn circuits in Arduino and Tinkercad, design a circuit, code, solder, design and build a case for our prototype, resolder, model on paper the 5 relationships of interest to us, and create hypotheses around these relationships, collect data from which we could create a linear regression, then model in AnyLogic to verify that it reflects the data and validate that it reflected the real-world outcomes, and reflect on whether or not the hypotheses that we hypothesized were correct. Discussion. For our sensor case, we chose not to 3D print, but instead create our own prototype case from materials and products that could be bought at stores and modified because we had a time and fiscal budget. We also inserted foam padding to make sure that it wouldn't move around. We then cut a USB hole to allow data collection from an external computer. And finally, we added a rubber seal to the case to allow for better water resistance. What worked well about this case is that the clear top allowed for data collection inside of the case, which better protects the prototype. What did not work well is that there was a USB cable hole, which meant that the case was not waterproof, only water resistant. Paper model. Our relationships of interest for this project were the time of day on light, the time of day on temperature, outdoor light on temperature, indoor light on temperature, and outdoor light on indoor light. We chose these relationships because all of the parameters were something that we could actually measure with our prototype. We did a polarity table. Our first hypothesis was that later in the day would yield greater light values. Our second hypothesis was that later in the day would result greater temperature values from the temperature sensor. Our third hypothesis was that outside light would make temperature values higher. Our fourth hypothesis is that inside an artificial light would make temperature values higher. And our fifth and final hypothesis was that outside light would make inside light values higher. This is our causal loop diagram. Off of this, we based our system dynamics, where our stocks are, in this case, are temperature and light values, and our flows are often changes in light or changes in time. Were our paper models correct? I would say about 50-50. We need some dynamic variables inputted into the system to account for uncertainties. For those tests, we got unclear data that didn't suggest a relationship. Our hypotheses about time of day and outdoor light and time of day and temperature were correct. Our one astoundingly incorrect hypothesis was that outdoor light had a good effect or a noticeable effect by our prototype on temperature.
For sensing, we determine our testing criteria by locations or time. For example, the indoor and outdoor data of the underquad, like similar time but at different locations. The length of time of our data collection is 5 minutes to 10 minutes. What didn't go well was that the temperature sensor is of poor quality, so it was sensing sometimes only 2 changing values. What went well is that it was challenging, so we learned a lot. Our data collection conditions, one is UT's undersquad ER, balcony outside of a condo, and inside and outside of UT understore. Linear regression, we use Excel data analysis. Additionally, the yard for daytime light versus time data. See that the model has non-independent errors turns. Linear model is not applicable for this hypothesis. The temperature has a very low R-square value. Based on the residual plot, there is not a linear relationship for this model because the errors are non-independent. Condition B, outside of EER. Temperature versus time plots are these. The residual plots shown non-independent variance. Linear regression is not suitable for this hypothesis. Again, the residual plot represents the non-independent variance, which linear model is not suitable for this hypothesis. So this is condition C. outside of a balcony on the fourth floor at night. This is a temperature versus time data. So you can see again, it doesn't have independent arrows, so linear model is not suitable for the hypothesis. Again, this one is not suitable for linear model because the arrow turns are independent. So this is convention D in Thorne. So as you can see here, again, indoor light temperature plot shows non-independent arrow variance. So again, it's not applicable for the hypothesis. So this one is outside of the honor squad. So again, residual plot has non-independent arrow turns, so which means it is not applicable for linear modeling. Again, it is not applicable for linear modeling for the indoor and outdoor light data. Thank you.
How can we use linear regression? We make models. Models help us use our data and trends to interpret relationships and their effects as a whole to better understand the world. To make a smarter world, remember, we are Smart World Systems, Inc. We created models in AnyLogic. The coefficient was the changing rate of time at noon, which decreased lumens every second. Comparing the model graph to the linear regression approximation graph, the model appears to be relatively accurate. Quality of the sensor as well is impacting the accuracy of the data. The model of time impacting light at night seems more accurate. This makes sense though, because the light is more constant at night, time of day at noon, impacting temperature sensed. Even though the data points seem far from the line of fit at some points, this error is only 0.5 degrees Celsius maximum. The error would be significant if the data is important for optimizing chemical reactions at specific temperatures, and the data at night is definitely much more precise and accurate. In sunlight and temperature, the sunlight increases causes the temperature to increase. Looking at the artificial light's impact on temperature, as the artificial light lumens increase, the temperature dramatically decreases. Light outdoors impact on light sensed indoors. The model does not seem accurate. There are a few outliers in the data points, and the R-squared value that's far from 1 also leads to the conclusion that this model is not accurate in explaining the real-world relationship between outdoor and indoor light.